Hello guys, and welcome back to another video tutorial for chemistry. And this video tutorial is going to be focusing on our second topic from our previous video tutorial, which we learned how to deduce chemical formulas, how to balance chemical equations, and how to convert word equations to chemical equations. Today we're going to be continuing from there by looking at how synthesis and decomposition reactions occur. So I'm going to open up the PowerPoint slide. Again, if you guys are interested in having these PowerPoint slides, I can be able to post that, like I said in my previous video tutorial, on Google Drive and share it with you guys in the description box down below. So if you'd like that, just let me know in comments. So we'll start off with our PowerPoint slide that I've made today for us, which is focusing on the synthesis and decomposition of chemical reactions. We are not going to be looking at reactivity series as of yet. We'll be looking at that in our next chemistry video tutorial that will be focusing on single and double displacements of reactions. So that's where we're kind of going to use this reactivity series. So we'll be looking at that in our next video tutorial. So today's lesson, as usual, I always have this periodic table available on the slide because we might use that, and also this polyatomic ionic periodic table as well. First thing we're going to understand is what is synthesis reaction. So synthesis basically means where two reactants combine to form one large or complex product, or you could say compound. So for this to occur, the reactants must of course first collide, which means they break their existing bonds and between their atoms, and they form new bonds or new chemical compounds. For example, if you look here at this simple illustration, you can see that there is A plus B, which gives you AB. So this is a simple example of how a synthesis reaction would occur, where you'd have reactants reacting together, combining together to give you a mixed compound or a product. So synthesis reaction, if you look at how basically synthesis reaction works, so that you can form a chemical formula or you can be able to produce a chemical compound. For example, here we have two reactants, magnesium and oxygen gas. When we want to form synthesis reaction, we say magnesium plus oxygen gas, as you can see here in step 2. And of course, now we need to decide what the subscript numbers are going to be based on the ionic charges for each element. So basically, we know that the ionic charges for magnesium is 2 plus and oxygen is 2 minus. So the 2 cancel out. So that gives you a chemical formula of MgO, magnesium oxide. So this simple chemical equation where you have magnesium plus oxygen gas on the left side to produce magnesium oxide, is what we consider as a synthesis reaction. So here it talks about whenever we create a synthesis reaction, of course, we have to consider the fact that we must balance the equation of all. After all, synthesis reaction is where we have reactants reacting together to produce a product. So we also have to balance that chemical equation. So if you look at this chemical equation that we have for magnesium and oxygen reacting together, where we get magnesium oxide, we have to balance both sides. So if you look here, we have one atom of magnesium and we have 2 atoms of oxygen on the left side, which we can say on the reactant side. And on the product side, we have 1 atom of magnesium, but we have 1 atom of oxygen, so it's not balanced. So obviously that means we'd have to put 2 here for magnesium in front of the magnesium oxide. So we have 2 atoms of magnesium, and then we have to put a 2 here again. So it's balanced, and we now have 2 atoms of oxygen. So it's pretty much what you can see on step 4. So we look at synthesis reaction that occurs between nonmetals and hydrogen. So synthesis reactions between nonmetals basically is we apply the same pattern of synthesis since the reactants are nonmetals, which means the product will obviously be molecular compounds. For example, if we look at synthesis reactions with hydrogen or that involve hydrogen, most of the group 1 elements form ionic compounds when they bond with each other. And for example, hydrogen, however, is different. It usually forms molecular compounds, not ionic compounds. So molecular compounds, they're made up of atoms and not ions. So that's the difference between molecular and ionic compounds. So most of the time, group 1 elements would form ionic compounds when they react with other elements. However, since hydrogen does also fall in group 1, it is a bit different because it is not a metallic. It's not a compound, an element that can react with other reactants to form an ionic compound. Instead, it forms a molecular compound, which is made up of atoms rather than ions. So, however, it says the ionic charges are still useful because they predict the products of the synthesis reaction. Of course, whenever you have two reactants reacting with themselves, you need to know what the product is and you need to get the right product. So this is where you apply what we learned in our previous video tutorial of how you can successfully determine the chemical formula of two elements or two reactants reacting together. So the ionic charges are necessary because that helps to determine what the chemical formula would be for that compound. So here we have, for example, the reaction between hydrogen and chlorine gas. So here we can see that hydrogen and chlorine are the reactants, and of course they form hydrochloric acid. So that again has to do with the ionic charges, which then help us determine what the product chemical formula would be, which in this case is hydrochloric acid. To represent hydrogen, whenever you are reacting it with anything, you have to write it as H2, not just H. So as you can see here, and then chlorine gas as well, Cl2. So H2 and Cl2, both are gases. As you can see, they're non-metals, so they produce hydrochloric acid. And how we know the formula is HCl is because we have no subscripts numbers, because hydrogen has a charge of +1 and chlorine has a charge of -1. So +1 -1 is a 0. So automatically you get the HCl. So to balance it, of course, as we said before, whenever you have a synthesis reaction, you must balance it. Since we have 2 atoms of hydrogen on the left side and 2 atoms of chlorine on the left side, that is on the reactant side, and then we just have 1 atom of each on the product side or on the right side, we have to balance it by putting a very simple 2 in front of HCl, which now says that hydrogen on the product side, which is on the right side, has 2 atoms, and chlorine has also 2 atoms, which then balance on the reactant side as well. Now, guys, we're going to be looking at synthesis reactions that don't involve hydrogen. So it says the products of synthesis reactions of non-metals other than hydrogen, which means other non-metals, are often depend on the reaction conditions. So, for example, 2 products are possible for the reaction of carbon with oxygen, depending on the availability of oxygen. So again, it depends on how much oxygen is available to produce a certain product, should I say, or compound when 2 reactants that are non-metals react together. So for example, here we can see carbon, which is solid, plus oxygen gas would give you carbon dioxide. So this is an example of a synthesis reaction that does not involve hydrogen, but also involves other non-metals. And so the only way to identify in this situation the reaction products is actually by performing chemical tests, so that you know the amount of oxygen, because when you perform chemical tests, you then know exactly what amount of oxygen is available to produce what kind of output. So synthesis reactions involving compounds. We also have synthesis reactions that does involve compounds, which means when 2 compounds react together to produce another or a new compound or new substance. For example, it says compounds, here's an example. So it says when carbon dioxide is bubbled into water, the 2 compounds react to form a new substance, and this new substance is what we call the carbonic acid, and this is what you can see as H2CO3, which is aqueous. So water is bubbled into carbon dioxide. As you can see, water being represented as an L liquid and carbon dioxide as a gas actually produces this new compound called the carbonic acid. I'm just going to skip this part, guys, because it then further explains to us more examples of where we have synthesis reactions that involve compounds. Now we're going to this part here, which is the next part before we do some examples, and this has to do with decomposition reactions. So we've understood synthesis reaction is where we have 2 reactants reacting together to form new products. Mostly we would have elements reacting together to form new products like compounds, or we even have compounds reacting together to form new substances or other new compounds. Here in decomposition reaction, it's the opposite. So decomposition reaction basically is a reaction that breaks down a large compound into smaller substances or substances. So decomposition is having a chemical compound being broken down into separate elements. So if we look at this example here, we can see that, again, they use the AB to represent. So it says AB is, decomposed into A plus B. So that means the chemical compound of AB is then broken down into A plus B. So normally with decomposition reactions, unlike with the, what we just saw, which is the, synthesis reaction. So with decomposition reactions, you normally have the chemical compound on the left side, which then breaks down into those reactants. But with synthesis reaction, you have the reactants on the left side. This example above, guys, is just an example that further gives you an example of how decomposition is formed with toluene, which is C7H5NO2 and 3. This is an explosive, so this is decomposed into these several elements and compounds: carbon and carbon monoxide, nitrogen, water, and energy is released. So I'm going to move on now to predicting the products of a decomposition reaction. So how do we determine the right products with the right amount of atoms when we decompose a chemical compound? So simple ionic compounds, for example, here it says potassium chloride can be decomposed into their elements. For example, potassium metal and chlorine gas are made industrially by passing electricity through molten potassium chloride. So if we were supposed to decompose potassium chloride, as you can see in this example, it's going to be breaking down into potassium and chlorine gas. But we also have to make sure that we have a balanced equation, which means a balanced amount of atoms on both sides. So this is achieving the law of conservation of mass, of course. So that means if you look at potassium chloride, we know the charges are plus. Potassium has a +1 and chloride has a ±1, or you could say chlorine. So of course that gives you KCl. But when it's broken down or decomposed, it gets you into potassium, which is normal K, and then chlorine gas, which is Cl2. So it's not balanced, obviously. So that means you would now have 2 atoms of chlorine here on the reactants side. And then on the product side, which is being decomposed, you just have 1. So that's why we have to put 2 behind the potassium chloride. So it's balanced for chlorine. And now you have 2 atoms of potassium, which again tells you have to put a 2 behind on the reactant sides for potassium. So this is essential. Again, the same method that you normally have to use with synthesis reaction, you'd also have to use with decomposition reaction of balancing the chemical equations. So we're going to look at a quick summary, guys, before we do some examples to understand this better. Here it says chemical reaction can be grouped according to the pattern of reactants and products in their chemical equations. In a synthesis reaction, 2 simple reactants combine to make a larger or more complex compound following the general pattern, which we saw before, where we have the reactants on the left side added together or combined to form the product. With a decomposition reaction, a complex compound is broken down into 2 or more simpler products. So we'd have the chemical compound on the left side, as we can see in this pattern of AB, and then would have it broken down into its separate reactants or separate elements. Now we have some questions we're going to be completing. I'm just going to open up a Jamboard so that we can do these questions as practice, and then you could still practice some more chemistry questions. If you would like me to be posting chemistry questions as well in the description for you to practice based on the topics we do on our video tutorials, then please let me know as comments, and I'll be able to do that as well. So I'm going to go open up Jamboard, and I'll just pause this for a minute. Okay, guys, so back here again. So we have some examples here, and this basically are some questions, and these questions are based on what we've just learned about synthesis and decomposition reactions. For the first question, it says, classify these reactions as synthesis or decomposition and justify your choice. I'm just going to open this with Google Slides because I need to copy the screenshot so we can do it as work on it together, and I can write on this. So I'll just open it on Google Slides, and I'll just copy this whole thing here. So, all right, so let's post it on the Jamboard. Okay, so, oops, I think I just copied the entire thing. Okay, so I can just maybe paste it. Let me try again, guys, and see. I think it's copying for me the entire thing. So this is actually the complete set of questions. I'm just going to zoom into what we need. So it doesn't matter. I'll just zoom it in. So for the first question, it asks us to identify whether these reactions are synthesis and decomposition. So if you guys remember, the pattern for synthesis is basically where you have A plus B, and it's basically giving you AB. So this was a synthesis reaction. So that's pretty much the pattern you need to follow to determine which one of these letters is a synthesis reaction and which one is a decomposition. So I'm going to put S in the brackets here. For synthesis, the pattern for decomposition was AB, which was the chemical compound, being broken down or decomposed into the reactants, which is where we had the A plus B. So we're going to use this pattern to determine the answers to the questions. So the first one is obviously going to be synthesis. So because we have aluminum reacting with bromide or bromine gas, and so we have aluminum bromide, so that's synthesis. Here we have hydrochloric acid. So this is being broken down into hydrogen and chlorine. So that's going to be decomposition. Again, you can just follow the pattern to understand this better. And then here we have calcium oxide and we have water. And again, this is where we have synthesis that involves chemical compounds. And you can see that they're, reacting together to form a new substance, which is calcium hydroxide. So this is also going to be considered as synthesis since it is reacting chemical compounds together. Here we have phosphorus and then we have oxygen gas. Again, we see that they react together to form phosphorus pentaoxide because we have 5 atoms, not molecules, 5 atoms of oxygen, but we have 2 molecules of phosphorus pentaoxide. Remember, if you wanted to consider it as molecules, then you'd have to represent it for the whole chemical formula. So in this case, this is an example of a synthesis reaction. Okay, so that's done. For question 2, it says predict the products of these synthesis reactions or synthesis or decomposition reactions. Write a balanced chemical equation. This is actually zinc, guys. So this is Zn. So this is zinc plus sulfur. And I think it's going to give us zinc sulfide because it says that we need to predict the product of these synthesis or decomposition. So some of these reactions from questions A to F are actually synthesis and some are decomposition. The first one, which is this one that we have here, so I'm just going to go to a new slide. So the first one is, I'm just going to change pen colors. We have zinc and it's reacting with sulfur and it's going to give us obviously zinc sulfide. Okay, and again, remember, we can determine this by the ionic charges. If you go back again to the slide and you go to the beginning and you look at the polyatomic periodic table, you can see that zinc has a charge of +2 and then sulfur or sulfide, I'm just going to find where that is, sulfur sulfide, it will have a charge of 2- as well. Let me just find it. Kind of hard to find stuff sometimes. Just gonna find it. I'm gonna pause and try to get it without wasting the video too much time on the video. So I'm just gonna find it since I can't. Sulfur. I think I see sulfate, but not sulfide. Sulfur. It's gonna have sulfur. Okay, let me try to search it up in a few minutes. Yep, there, I found it, guys. So this is it here. It's on 16. It's on number 16, sulfide. So it's 2-. So zinc has, so how did we determine this product? So basically, zinc has an ionic charge of 2+, and sulfide has an ionic charge of 2-. So obviously, 2 plus 2-, or 2 plus 2-. So if you cancel these out or you simplify, it's basically like you're saying 2 minus 2 because you have +2 minus 2. So that gives you a 0. So they cancel out. And so you get your chemical formula as ZnS. So zinc sulfide. All right, moving on to the next one. The next one is, I'm just going to go back to our sheet here. So the next question is for calcium chloride. So you can see that for example B, it is not, this example here is not a synthesis reaction, but rather a decomposition reaction. So that means for this, where you have calcium chloride, since it is a decomposition reaction, it means that this chemical compound is going to decompose into its reactants or into separate elements. So that's going to give us calcium, of course, and then chlorine gas. So this is what's going to be like. And so now we have to always look at our chemical equation to see if it's balanced. And I forgot to mention that with the zinc sulfide, it's always important to look and see if it's balanced. So this one was already balanced, so we didn't need to do anything. So it was balanced because there was 1 atom of zinc and 1 atom of zinc on the reactant and product side, 1 atom of sulfur, 1 atom of sulfur on the product and reactant side. Now, this is what we have to look as well for calcium chloride. Since this is a decomposition reaction, we have to see if this is balanced, and if it is not, we need to balance it. So what we can see is calcium chloride is decomposed into calcium and chlorine gas. We have 1 atom of calcium on the product side. We have 1 atom of calcium on the reactant side. We have 2 atoms of chlorine gas on the product side, and we have 2 atoms of chlorine gas on the reactant side. So this equation is also balanced. We don't need to do anything for this decomposition reaction. All right, guys, let's look at the next one. So the next one is we have two compounds reacting, which is ammonia and hydrochloric acid. So let's write it out here. So in this case, we have ammonia and we have hydrochloric acid. So we write the chemical formula, ammonia. So this is obviously telling us it's a synthesis reaction because we can see it follows this pattern of A plus B, which basically gives you AB. And now we need to determine what the product is going to be, and we need to make sure we have the equation balanced, which means the number of atoms on the reactants and product side as they react will be the same as they are produced. So law of conservation of mass. So here, what we need to do is first ammonia, which is NH3, plus hydrochloric acid, which is HCl, is obviously going to give us ammonium chloride because, we have these two compounds reacting together. So we don't have anything else other than ammonium chloride being produced. So it's going to give us NH4 Cl that is being produced. So this reaction is also balanced because if you look at the products, the number of atoms for each element individually on the reactant and product side, you're going to see it's equal. Nitrogen has one atom on the reactant side. On the product side, it has one atom. Hydrogen has 3 atoms here, but has +1 here, which gives you a 4. So 3 plus the 1, which you get a 4. And so that's the same number of atoms we have on the product side as well. And then we also have chlorine, which basically is 1 atom of chlorine on the reactant side, and it gives us 1 atom of chlorine on the product side. So I'm just going to write it down here. So which means that this equation is also balanced. All right, guys, let's look at some more examples. So I'm going to go back and we'll do one more, and then we'll move into our last question for our video tutorial today. So the next one we're going to look at is example D, and this one is for potassium oxide. So potassium oxide, we can see that this is also a decomposition reaction because this has to decompose into separate elements or separate products, simpler products. So let's go back and do this one. So we'll do potassium oxide. So we have the chemical formula of K2O, and this is a decomposition. Remember, this one was a synthesis. So this is a decomposition reaction. So this decomposes into potassium, and it decomposes as well into oxygen gas. So potassium and oxygen gas react to form potassium oxide in the, inversional sense, if you look at this backwards. So here we have to determine if the chemical equation is balanced after we decompose this compound. So what we see is for potassium oxide, we can see that potassium, there are 2 atoms of potassium on the product side, and there is 1 atom of oxygen on the product side as well. So that means if we look at the reactant side, we can see that there's only 1 atom of potassium on the reactant side, and there are 2 atoms of oxygen on the product side. So it's definitely not balanced. So that means we need to start by at least balancing the potassium on the reactant side. So that means if we put 2 at the back of potassium, that will be 1 times 2. So that means now potassium has 2 atoms, so it's balanced. So 2 atoms of potassium on the product side, reactant side, and 2 atoms of potassium on the product side. But then that means that we also have to check oxygen, because oxygen here on the reactant side is 2, but on the product side is 1. So if we wanted to make this 2, we times it by 2. That means we have to put it here. So now it becomes 2 atoms of oxygen on the product side. But the problem is now it becomes 4 atoms of potassium, because 2 times 2 will give you 4. So it becomes 4, not 2 anymore on the product side, which doesn't balance the number of atoms of potassium on the reactant side. So which means that we're not supposed to put 2 here so we can balance this, but instead we should put 4 so that we have 4 atoms as well of potassium on the reactant side. So this means we're going to put 4 here, guys. So that means we now have 4 atoms of potassium on the reactant side, which then balances with the 4 atoms of potassium on the product side. So this equation is now balanced. So finally, your result is going to be 2. So this is the final result, is going to be 2K2O. So this is 2 molecules of potassium oxide. That's going to give you K, and then that's going to give you O2. So 4 molecules of potassium with 2 atoms of oxygen. Or you could say 4 atoms of potassium, with 2 atoms of oxygen. So molecules would just be because I'm representing the whole chemical compound. So this is the answer to this question, guys. So now we're going to go and look at our last question for our tutorial video, and we're going to end it here. So the last question we're going to take is question 3. If you would like, guys, I can post the remaining questions for you to try on this topic. So as a practice, just let me know in the comment section, and I'll try my best to post in some more questions. So question 3 says, hydrogen peroxide forms gas bubbles when it is added to blood. And we know, of course, inside of the blood, the hemoglobin, we have the oxygen gas that moves around as well. So that gives you an idea of what's happening. And it says hydrogen peroxide forms. So which means that there's already a decomposition happening, because it says hydrogen peroxide, which has a chemical formula as H2O2, forms gases. So it produces these gases, bubbles, when reacted with blood. And they said the other reaction product is water. So it also tells you what the other reactant is going to be with oxygen, which is obviously water, once hydrogen peroxide is decomposed when reacted with blood. So it says, inserting a glowing splint into a sample of this gas causes the splint to relight. Identify the gas. So if you guys have done a chemical experiment before, you know that whenever a gas basically relits is when oxygen is present. So obviously, since we know that hydrogen peroxide is decomposing or forms gas bubbles when it is added to blood, we know that inside of blood we have oxygen. So that definitely is going to give us. So guys, as I was saying, I was mentioning that the gas that would produce the splint to relight obviously would be oxygen, and that would be the answer for question A. So question A is going to be oxygen gas, because that's what would cause the splint to relight, since hydrogen peroxide is added to blood, and blood does contain oxygen. And the type of reaction this is, since we have hydrogen peroxide forming gas bubbles, is going to be decomposition reaction. Obviously, it says forms, that's the key word, so you know it's creating a reaction. I mean, it's decomposing into reactants, which is basically going to be like this. It's going to be H2O2, so if we represent this in the chemical formula, so since this is decomposition, it forms, as they said, bubbles, so that means oxygen gas is, of course, going to be formed. And then it also says the other reaction product is water, so also with water. So oxygen and water, you can write water plus oxygen, however you like. So this kind of reaction obviously is what we call the decomposition reaction. And so then the next thing we're going to be looking at, so we've answered question B. The last question is question C. It says, write a balanced chemical equation for this reaction. So we've just done that now. We've said hydrogen peroxide, which forms gas bubbles. So hydrogen peroxide is decomposed into gas bubbles represented by oxygen gas, and of course the other reaction product, which is water. To balance this chemical equation, we look at the number of atoms we have. So we have 2 atoms of hydrogen on the product side, and we have 2 atoms of hydrogen on the reactant side. We have 2 atoms of oxygen on the product side, and we have 3 atoms of oxygen, which is 2 plus this one here on the reaction side. So that means it's not balanced. We need to do something to balance it. What we could do, of course, is we could say, so let's write it out as this way. I'm just going to go into a new slide so you guys can see properly. So this is the chemical reaction that we have. So this is hydrogen peroxide is decomposing into oxygen gas bubbles being formed with water. So what I was saying was the number of atoms we have. For hydrogen on the product side, we have 2, and oxygen for hydrogen, we have 2 atoms on the product side, and oxygen, we have 2 atoms. So that means on the reactant side, oxygen is also 2 atoms, and hydrogen is 2, oxygen is 2 plus 1, guys, which makes it 3. So 2 plus 1, which is equal to 3. And then hydrogen is equal to 2 atoms. So we need to balance this. Hydrogen is balanced on the product side and on the reactant side, but the problem is oxygen is not, because we have 3 atoms of oxygen on the reactant side and just 2 on the product side. What we could do is, remember the key of what we always do to balance equations is try to get an even number. So the even number, we could say the even multiple that is common for both 3 and 2 is 6. So we could say, for example, here we could add a 2 in front of this, in front of water. Not even that, because we're trying to get a total number of atoms on both the reactants and product sides for oxygen to be even. So we could put a 2 in here. And if we put a 2 in front of water, that would mean that we now have a total of 2 plus 2 oxygen atoms two oxygen atoms here and 2 oxygen atoms here, which means we now have 4. So that makes sense. That's even. That's an even number. That's what we want, so we can balance it easily. So we now have 4 atoms of oxygen because we have 2 atoms plus 2 atoms here, which again is on water. So that gives you a total of 4. So now that we have 4 atoms of oxygen on the reactant side, we can easily establish 4 atoms of oxygen on the product side as well. If we put a 2 in front of hydrogen peroxide, we now have 2 times 2. So 2 times this 2 subscript here, subscript number, which now gives us a 4. So that means oxygen is now also 4 atoms on the product side. But the problem is hydrogen is now no longer 2, but because we have a 2 as well representing for hydrogen, it is also going to be a 4. So because 2 times 2, which is the 2 atoms that we just put for oxygen, also affects hydrogen, which gives 4. So since we have 2, we have 4 atoms of hydrogen on the product side, 4 atoms of oxygen on the product side. If you look now, the change that you've done where you added 2 in front of the water, which affected the oxygen, also affected the hydrogen, because we now have 2 times 2 atoms of hydrogen, which is 4. So this equation is now balanced. So eventually we have our 4 atoms on both sides. So your final equation would look like this. It's 2 molecules of hydrogen peroxide, or you could say 4 atoms of hydrogen, 4 atoms of oxygen. So that's your hydrogen peroxide. And that will decompose into 2 atoms of oxygen here. And we get our 2 molecules of water, or you could say 4 atoms of hydrogen as well, and then 2 atoms of oxygen. So this is going to be the final product, guys. So this is an example of a decomposition reaction. I'm just going to write what this is. So this is represented with, remember, you always have to represent what each chemical compound or element is in your equation. So water is liquid. So this is L, by the way, guys. It looks like an E, but it's actually an L. So this is L, representing liquid for water. And oxygen, of course, is the gas bubbles that was reacted or formed with hydrogen peroxide. And then here, hydrogen peroxide is aqueous. So we represent it as an AQ. Okay, so it's always important to describe what each product or chemical compound or reactant is in your chemical equation. We're going to stop here, guys, for today. We have successfully come to the end of our PowerPoint slide and our unit topic, which is synthesis and decomposition reaction. We have completed all the 3 questions that I wanted to do with you guys. And if you would like any more questions to do as practice, please let me know in the comment section and I'll do them. For now, this is where I end. You can check out my videos in my previous video tutorials so you can continue, or you can watch what I've done previously, and that could help you out. Have a great day, everyone, and I'll see you next time. Take care.